begin with a word of prayer. So, Heavenly Father, we thank you for this day, and I just thank you for the students. Just ask you to bless our work today, Lord. In your name I pray. Amen. So, yes, as promised, I was going to try to give you guys an example of something a little bit out there. And so this is actually taken from Manifolds, Tensors, and Forms, an introduction for mathematicians and physicists, which seems like it may be an inappropriate source to use for this class, but I think you'll find out that it's not. So let's see here. I have a handout which is in legal size because I didn't feel like fighting with the copier. So one for you, one for you, one for you, and sorry, Liam, but because you won't reschedule, I'm forced to give you this.
Because I won't reschedule?
Yeah. Actually, it's just because I think the copier ran out of legal size. These are only marginally helpful. Only marginally helpful what I just sent to you, gave you. But I do have a PDF. I'll post the PDF in course content so you can see what you're missing. All right. And I do have like half of the regular sized one.
What's the difference?
The difference is it's missing a page, and you can see where the copying machine went into an error mode at the end. All right. So.
This one's missing half the chapter on elementary homology theory. I don't think I'll be able to understand.
Liam won't be able to cope with that.
All right. So the first page is just the 2 pages in this book, which are about exact sequences and short exact sequences, the interplay between a short exact sequence and having a section or talking about the thing splitting. This is I gave you links to some videos where I talked about this material from the perspective of Dummett and Foote. But I have a suspicion that this is a helpful second thing just to look at if you're a little bit like you look at Dummett and Foote and you're just kind of like, I don't get it. Maybe reading these 2 pages will help. All right? That's actually not what we're talking about today. But I thought while I was at it, I should copy it for you. So page 2 is on elementary, chapter 5 in this book, elementary homology theory. And I suppose, since I have a book, I could do I do need this back at the end. So you don't care? Okay. Yeah, because I don't want to scan this again. Wait a minute. No, you can have this because I just remembered I have a PDF of it, so it doesn't matter. You can have that. We'll just persecute Liam. Seems like the right thing to do. Actually, this is from a statistical perspective, a rather unusual situation in here. All right. So let me just kind of give you the big picture of what we're trying to do here. Homology is, so you have some space, all right? And you'd like to describe certain what are called topological or perhaps geometric features of the space, all right? In some sense, the abstract sense of its shape, right? So homology is one way we can calculate something about the space something about a space, all right? And so essentially the idea is that we can take the space that we're looking at and we can form what's called the triangulation of the space, all right? And from that triangulation, we can calculate what's called the homology. So the homology corresponding to the calculation, it gives us this sequence of in this book, vector spaces. And the dimension of those vector spaces says something about the shape of the underlying space. So let's just, I think, that's kind of just a sketch of the idea. But let's just get into it. So he starts by defining a convex set. Then he talks about, so here's his definition. C. What? So I think that's supposed to be subset. C is a subset of Rn. He's got element. That doesn't make any sense to me. C, a subset of Rn, is convex. Let's go with subset. If for all x and y in Rn, oh, in C rather, the line segment and so here's the line segment, x, y, which is by definition tx plus 1 minus t times y, 0 less than or equal to t less than or equal to 1. I don't know if you've ever seen this notation before, but a notation which is often useful in this kind of context is to generalize the meaning of closed interval to like a line segment. So, why not? So, oh, and what does it mean for it to be convex? What condition do I need in the line segment? Here, I'm going to give you something that's not convex versus here's something that's convex. So pick a point x, pick a point y, pick a point x, pick a point y. You see that if you look at the line segment connecting x and y, in the right one, what can you say about it? Versus this one, right? So over here, xy is not a subset of C. Over here, xy is a subset of C, right? So this is the meaning of convex. If you can take a point, any pair of points in a set, and the line segment connecting those points is in the set again, it's convex. You know, it's a kind of funny thing. This is a very ubiquitous mathematical concept that somehow gets left out of elementary courses. Have you ever talked about this before? Linear, if I was, misbehaving a little bit more than I do. Mm-mm.
Are you talking about in the sense of like how to define convex with line segments?
Yeah.
No, I've heard.
Yeah. So, next up, the convex hull of a set U, denoted convex, is the smallest convex set containing U. So, man. Again. So you can talk about, for U, a subset of Rn, then how do you say it? Conv equals smallest convex set containing U. What is it? Aha! I did have a homework in linear about it. So you remember a convex hull? Yes. The interesting thing is, you can actually, there's actually kind of very nice results about convex sets, which are natural to talk about in linear. They're a little bit off the edge of what I test on in linear, but they're very similar in spirit. In fact, so that, like, for example, the convex hull, you could look at it as the intersection of all convex sets which contain U. In the same way you could think about the, I think the span of a set of vectors could be viewed as the intersection of all possible subspaces containing said vectors. So like definition of span, definition of convex hull, very much the same if we take a set theoretic viewpoint. I really want to move on. This is not the central thrust of what we're doing at all, just terminology at the moment. But fine, while I'm at it, what would the convex hull of this thing look like? What's the smallest convex set containing my, what is this thing? I don't know what this thing is.
It would be a straight line from the top of the right to the top of the left.
Yes. Right, so you're just fill that in right there, something like that, right? And then that would be fill. I mean, so the original C was just the, I don't know what this thing is, this the bended bean. But then if we filled it in, then if we fill in this gap here, then you got any line segment between any 2 points in the filled in thing. Right. Okay. Now, a polytope is the convex hull of a finite set of points. That was the whole reason we talk about this definition. A polytope is the convex hull of a finite set of points. All right. So can we, I mean, we can do some examples of that, right? Did any of you guys put this up here? No. It's hilarious because it's vaguely related to what I'm doing. It was just on the board.
Someone in a English novel wrote that.
Isn't that funny? So if we take 2 points, what's that? Oh, if we take 2 points, right, what's the convex hull of that? The line segment connecting the, exactly. If I have 3 points, what's the convex hull of these? Right, the fill in the triangle like that. Right. If I had, you know, in 3 dimensions, let's say, I'm trying to do these on the, I'm trying, you know, what's the rule about drawing in 3 dimensions? What do you draw first, axes or points? Oh, just do, the first rule of drawing in 3 dimensions is just draw 2D. Yeah, but if I'm going to try to superpose an axis on it, you draw the axis first, then you add points, is my point. Yeah. So, but I agree with you, start with the rectangle, and then from that, you know, you can build, if I was not, something like, okay, so just these points, right? These points, these points are the finite set of points. What's the polytope, which is the convex hull of those? It's the cube, right? So clearly, convex hulls, lots and lots of stuff, right? And it's a solid cube too, right? I mean, it's got to connect all line segments within there. Yeah. All right. What's exercise 5.1 say? It says take a finite set of points in Rn and take a linear combination of them such that the weights of the linear combination are positive, or excuse me, not negative, and sum to 1. Then P is a convex combination of the points in S. Show that the convex hull is precisely the set of convex combinations of points in S. Use induction on K. In other words, what exercise 5.1 does is it gives you a stone-cold formula for the convex hull. It says that the convex hull of a finite set of points S, it's just equal to the sum of, let's say, Ti, Si, I equals 1 to n, such that Ti greater than or equal to 0, and the sum, I equals 1 to n of T sub I is equal to 1. And here S is, instead of n, let me use m, as in mommy. So if I take a set of m points in Rn, I can form the convex hull by taking these sorts of linear combinations of the points. That's just what I've been doing geometrically. The vertices correspond to like all of the s's being 0 except for the one in question. And then you just let the coefficients, the s, or rather the coefficients, the t sub 1, t sub 2, t sub m, vary between 0 and 1 to sort of sketch out the middle of the shape, right? If this is S1, this is S2, and this is S3, right? You can see this in action. This point in the middle, what is it? It's 1/3 of S1 plus S2 plus S3, right? The geometric average. And of course, 1/3 plus 1/3 plus 1/3 is otherwise known as is 1, right? If you took the sum of the weights to be larger than 1, it would put you outside of where you want to be. And you can, but anyway, that may have been the linear problem. This is definitely what inspired that linear problem, by the way, though. Okay? All right, page 1. Great. Now, page 2, or 140. He says, let V be an Rn, let A be a real number, and let G be the usual Euclidean metric. Any set of the form, all right. Sad, it has to go. I'm on page 140, which may have gotten eaten by the copier. I don't know. Sorry about that. It's the figure 5.1 and then figure 5.2. Okay. So definition, G going from Rn, it goes from Rn cross Rn to Rn again, not Rn, just R again. And here's the definition. G of xy is, okay, we could do x transpose y, or if you like, we could do x dot y. It's just the ordinary Euclidean dot product, all right? That's what he means by Euclidean metric. It's just the dot product, okay? And he defines in a fine hyperplane. He says we can make it have the following form, x in Rn such that x dot v is equal to a. He says this determines two closed half spaces. So the closed half spaces, namely x dot v greater than or equal to a, or x dot v less than or equal to a. Those are going to be the two closed half spaces. Let's look at a specific example in 3 dimensions to make this make more sense, okay? Because I know you guys probably are not terribly enthused with this definition. Okay, so we're going to let, we want to look at x, y, z, an element of R3, such that, well, x, y, z dotted with, let's say, I don't know, n1, n2, n3 equals to, fine, I'll stick with his a. So this would be an example of an affine hyperplane where I'm taking this to be the v. And I'm taking x, y, z to be the point in Rn. What is that equation? Can you recognize it? You guys have all had calculus 3, right? Calc 3? Calc 3. Calc 3? Haha, yes. It does, yeah, well, it is a dot product. I don't dispute that. Yes, yeah. Oh, I see. You've grown so mistrusting. It's some sort of abstract dot product. No, I literally mean the dot product from calculus 3. In R3, no less. What is this? This is the equation of a? Nope, not sphere. No. If I said x plus 2y plus 3z equals to 4, you'd tell me what it is, right? This is the equation of a plane, right? The reason it's affine is because it doesn't have to go through the origin, right? It could be parallel shifted off the origin. If we put a equals to 0, it would just give us a good, honest to goodness plane through the origin, right? Subspace of R3. So the point here is that this vector v serves as the normal to the affine hyperplane. All right. So this is, it has, this is an affine hyperplane with normal v, and so you can either be above or below the plane, right? That gives you two closed half spaces, right? No? Yes? You? Does it make sense?
Yeah.
If I take a plane, it divides R3 into two sides. Okay, great. No, hopefully nothing controversial there.
So like with that example plane, it's not allowed to go through the origin, right? That plane does not go through the origin. Like x plus 2y plus 3z equals 4.
Does that go through the origin? No, yeah, you're right, it does not. Because if I plug in 0, 0, 0,
Right.
no, it doesn't give 4, right? My point is, if I had some minuses, it's conceivable I could have a 4 here, and if I had the right kind of, wait a minute. No, the only way to get the origin is to put a 0 over here, right? Yeah. Never mind, I'm thinking of something else. Okay, so we could look at an example here. You could look at the closed half space like this. Say z greater than or equal to 1. This would be a closed half space like above z equals to 1. The supporting affine hyperplane would be what? In this case, it's just a plane. It would just be z equals to 1, right? Or in the language of, this would be, we could write it, if we wanted to be more confusing, we could say, it's x, y, z in R3 such that x, y, z dotted with 0, 0, 1 is equal to 1, I suppose. Okay, so the idea here is just that we can talk about a plane in n dimensions. I mean, to really sell this more, I should say, okay, how about R4 or something, right? Or maybe even R2, but I'll do R4. We could set v equals to, say, 1, 1, 1, 1, and we could put the a equals to 3, and that would give us the affine hyperplane in R4 of the equation, x1 plus x2 plus x3 plus x4 equals to 3, right? And the set, all such x1, x2, x3, x4 would form the affine hyperplane in R4 that's built from the vector v equal to 1, 1, 1, 1, and a equals to, what did I say, 3. The point is, the concept of a plane, it's not unique to R3 or R2. You can do this in any dimensions, right? And whenever you do that, it's going to divide Rn into two pieces, right? Above the plane, below the plane, corresponding mathematically to greater than or equal to a or less than or equal to a. All right. Okay, great. So this is his concept of supporting hyperplane of a n-dimensional polytope. All right. Now, here's his definition. He says the affine hyperplane H is a supporting hyperplane of an n-dimensional polytope if the polytope P meets H on some non-empty set and P is confined to one of the half spaces determined by H. I have trouble reading. Look. This is essentially that sculpting process maybe you thought about in Calculus 3, right? If you, you could start out with this being, we could look at this space, right? And so here, there's the affine hyperplane, just R2, because I don't want to draw this in R3, but here's the idea. This would be like affine hyperplane 1. So here's the polytope here, right? Polytope, it's the convex hull of this set of 4 points, right? So here's affine hyperplane 1, affine hyperplane 2, affine hyperplane 3, affine hyperplane 4, right? These are all supporting hyperplanes, and the polytope should be in between all of them, right? Like we can, this is something he's trying to point out. He says any set of the form P intersect H, where H is a supporting hyperplane, is called a face of the polytope. All right, so the intersection of P, right? The intersection of P and H1 is this right here, right? So this is face 1. The intersection of P and H2 is the line segment which connects those vertices, right? Right here, face 2. Right? So do you see, this definition allows us to define the face of a polytope in terms of the intersection of the polytope with its supporting hyperplanes. Right? A face of the polytope is going to be an intersection of the polytope with one of its supporting hyperplanes. Yeah?
So it's still a hyperplane, even if, like, in this case, that's just a line.
Right, right. When I say hyperplane, it could be a line, it could be an honest-to-goodness plane, it could be a volume, like my R4 example, that's actually a volume. It's a three-dimensional space, to be true. Okay. So he says the definition allows for F equals to P, all other, sorry, I'm missing words here. Any set F of the form P intersect H, where H is a supporting hyperplane of P, it's called the face of P. Great. The definition allows for F equals to P. All other faces are proper. Definition allows for F equals to P. What? Let's go on.
So like if it was just a line segment, and that was what you were working with,
Oh.
the hyperplane was the line segment that was
Very good. So that wouldn't be proper. Is the point?
it would.
I think he's.
Well, there wouldn't be like a line segment because it's only one line.
He says the definition. Yeah. Well, he says the definition allows for F equals to P. All other faces are proper.
Okay.
So I think these are proper faces. I think that when we take the polytope formed by these, I believe that the, but still F is, what is F? Oh, F is the intersection with the, oh,
You could almost see that like
it's the whole thing, so it's F equals to P. Okay, I see, yeah.
So like if H1 was restricted,
This would be H1, right?
right? But if
None.
if H1 didn't exist, only existed in conjunction with P or whatever, then like that line segment of P would be like a non-proper face.
Like these ones.
Of H1, right?
Of P. We talk about faces of the polytope, not of the affine the bounding hyperplanes. All right. Anyway, honestly, I don't know. I got sucked into this. I don't know if it even matters to what we're doing, actually. But it's helpful to get this in our system, leading to the discussion I'm actually interested in. Okay. The dimension of a face is what? It's the dimension of the smallest defined subspace containing it. So, if we're talking about the polytope of the cube, that's useful for a second here, right? Yes. So what would the dimension of the face of the cube be? It would be, we could take this affine hyperplane, right? And then this would be the face that intersects that. Listen, long story short, guys, it's what your intuition says. What's the dimension of these faces? It's 1, right? If we were to look at this, what's the dimension? See, a face here, by the way, that's a face. Because if we take any line that does like that, that means that the endpoints are faces. What's the dimension of the endpoints? Wait a minute. Is that right? That seems wrong. I wanted the dimension of the endpoints to be 0. If I've said this properly. Oh, I made this confusing. Idiot. All right. Let me just write down some words and stop trying to ruin the lecture. All right. Yeah, that's what I should write down. The dimension of the face is the dimension of the smallest affine space containing it. A 0-dimensional face is a vertex of P. But I suppose that perhaps doesn't come from the I don't think it has anything to do with this picture I just drew here, okay? Let me stop that. All right. So yeah, what do you say, 0-dimensional? Good grief, I keep losing my place. 0-dimensional face is a vertex of P. What is a vertex of P? Yeah, did he define vertex in here anywhere? Yeah, I think a vertex should be one of the points in the finite set with which we're taking the convex hull of, right? So I believe that's the definition of a vertex. It's these are all vertices, I think. Okay, anyway, a one-dimensional face is an edge. An n-1-dimensional face is a facet. How do you say that? A facet, all right. The collection of all facets of a polytope is the boundary of the polytope, all right? The interior of a polytope is P minus its boundary. He says, because polytopes have facets or seats, they're also called polyhedra, which means many seats. He says, it is obvious that a polytope is the convex hull of its vertices, and that every face is just the convex hull of some subset of the vertices, but he's not going to prove that. Okay. Okay, so hopefully that gets us started in here. So what do we mean, definition? What does affinely independent mean? So we have a set of D points in Rn is so-called affinely independent. What's that mean? He tells us that means that the vectors, how's it go? P1 minus P0. What's next? P2 minus P0. What's next? Oh, kind of boring, isn't it? PD minus P0, all the way down, right? Is linearly independent as a set of vectors. in Rn. Definition, a simplex is the convex hull of an independent set of points. In fact, I've only put up independent sets of points on the board. My bad. How would I make them not independent and not change the hull?
Would it be like in R3,
Uh-huh.
points on the same line?
Right, I could just throw in some points like this for no particular reason. Yay, nothing, but those are redundant, right? I mean, those are already included in the convex hull of the blue points, right? So, yeah. So a simplex is the convex hull of an independent set of points, all right? That's a, this is a, he says brackets S to denote the simplex determined by the set S. He says if the size of the set S is d plus 1, then the dimension of S is d. So he introducing some notation here. Conv of S is equal to this. I mean, I don't know if this, well, I guess I better use this notation because I think he's going to use it extensively in what follows. But so that's the convex hull, right, which I've given a formula for, motivated by exercise 5.1, which I don't think I assigned, right? Did I assign it? I don't think I did. It's very disconcerting. People running by, waiting for zombies to follow or something. I don't know. I think I've watched too many movies. Let's see here. So the if the number of things in S is equal to d plus 1, then the dimension of the convex hull is equal to d. And that squares well with the things I've been saying up to this point, right? If you have 2 points, right, then that defines a line segment, right, which is one-dimensional. If you have 3 points and they're independent, it defines a 2-simplex, which of course is 2-dimensional, right? A triangle. What if you had, and then the context matters, right? If I had 4 points and they're in the plane, can that define a 3-simplex? If I have 4 points in the plane, oh, you notice this has, how many does this have? This has d things, right? How many things are in here? D plus 1 things. Notice that, the counting here, yeah? So what if I had 4 points, excuse me, what if I had, yeah, again, I think this is a simplex, right? What if I had 4 points in the plane? Is that, can we have 4 points in the plane which are, I mean, if this is P0 and this is P1 and this is P2 and this is P3, so like P1 minus P0 is this one, right? And here's P2 minus P0 is that one, right? P3 minus P0 is that one. Let me restate the question. Can you have 3 vectors in 2 dimensions which are linearly independent? You cannot, right? So the maximum dimension possible for a simplex in Rn is n. An n simplex is the biggest simplex that n dimensions can support. In R2, a 2 simplex is as big as it gets. But you could also have a 1 simplex or a 0 simplex, right? You could have like a regular polytope, polygon really, and its edges are 1-dimensional and its vertices are 0-dimensional. If you're in 3 dimensions, you can have essentially a solid with flat sides, right? A polyhedra. And its faces are 2-dimensional. The edges of those faces are 1-dimensional. The vertices of the polyhedra is 0-dimensional. Okay. Very good. All right. Okay. He says, because a subset of an independent set of points is itself independent, any proper subset of an finally independent set is a finally independent. That's kind of cool. So, in other words, if we were to, say, take some subset of these, if they're independent, then that's going to define a lower dimensional simplex. Okay? Which is not surprising if you think about 2 dimensions, right? If you got these 3 points, if they're not collinear, they define a 2 simplex, right? And if you take any pair of points in there, they define the 1 simplex, which is the line segment, which is the edge to the 2 simplex. All right. Finally, if, definition here I'm trying to get to, he says, any proper subset T of S determines a lower dimensional simplex T, which is necessarily a face of S. So if, he says, if the number of things in T, I'm writing number rather than vertical bars, okay? If the number of things in T is k plus 1, then the convex hull of T is a k-face of S. So suppose T is a subset of S. And here, this is a finally independent. All right. If you take in a finally independent set S, you take a subset of it T, all right? And if the number of things in T is k plus 1, then the convex hull of T is a so-called k-face of S, right? Like, oh, I heard you're going out with Melissa. What do you think? And you're like, I don't know. She's a k-face, something like that, something like that. No, too much of a stretch. It worked better with an all-male class for some reason. Let's see here. What's that? See, now I got to edit this. Anyway, so we have faces, and we have simplices. And so that brings us to the main definition. So I'm finally getting the main definition at the end of the lecture. Sorry about this. In my defense, this always happens. I knew it would take 2 days. That's why I set aside 2 days for this. It takes 2 days. So all of this, just to define a simplicial complex. A simplicial complex K, all right, is a finite collection of simplices satisfying 2 properties. Number 1, if S is an element of K, so suppose you've got a simplex in K, all right, and T is a subset of S, then the convex hull of T is also an element of K. Which is to say that every face of every simplex in K is once more again in K. Right? So if you've got a triangle that's part of the simplicial complex K, all of the edges and all of the vertices of that triangle are also in the simplicial complex. Them's the rules. And 2, for any pair of simplices in K, all right, the intersection of these two simplices is equal to the convex hull of their intersection. In other words, if two simplices meet, they do so along a mutual face. All right? So what's coming up next, and so sorry, I've kind of like buried the lead. The next lecture is where it actually gets interesting. Next lecture, I will show you how we can take a simplex like this and we're going to add an orientation, which is just to say put an order on the, order the edges, order the points, look at oriented faces and such. And we're going to see that we can build a boundary operator on this simplex. And that boundary operator then allows us to define the homology group corresponding to the simplex. And depending on what kind of space you're building, so a simplex for a space is basically just something that you could blow up to cover the space. So for example, a sphere, if you take the tetrahedron, that's an example. Tetrahedron's an example of a simplex, right? Because it's the union of the 4 equilateral triangles, each of which is a simplex. So this is a simplicial complex, which means a bunch of simplexes put together subject to these rules. So if I include the tetrahedron along with all of its faces, edges, and vertices, that's a simplicial complex. And you could blow that up, right? You could blow that up. You could kind of imagine expanding that to the sphere, all right? That would give you what's called a singular complex for the sphere. Theorem says that the homology for the singular complex is equal to the homology for the simplicial complex, so we can just calculate the homology for the tetrahedron, which is geometrically like simple, right? It will be. We'll see it next time. So you can actually write down the boundary map going from the faces to the edges, from the edges to the vertices, and then you can calculate the kernel and the image and the dimensions of those and figure out what the dimension of the, so it ends up being like the quotient of kernels and images, or vice versa. I forget at the moment, but we'll get into that next time. And so doing, we'll calculate the homology of a circle. The example I gave you guys in your homework is very much the same song and dance, except I let you calculate, I think, so your homework was taken from here. I believe exercise 5.3 is what I assigned you, which is to calculate the homology of a two-sphere. You're like, what does this have to do with modules, right? Well, what we're about to do is start looking at linear combinations, just integer linear, real linear combinations of faces and edges. And so that's like a formal linear combination. It's an example of, well, this actually ends up being an R module. I said Z module, but I was wrong. After all, there's thirds. Well, maybe it's still, well, verdict's not out yet whether or not this is really a Z module or not. It's possible he doesn't call it a Z module just because he's not trying to scare the audience. All right, like this is supposed to be a relatively low-level book as they go. The intended audience is a mixture of advanced undergrads in physics and advanced undergrads in math, or beginning graduate students. So it's not trying to be super sophisticated, it's just trying to impart the main intuition of this stuff. Anyway, I shut up.